I'm gonna record myself. Starting now. Cool, cool. So let's start with the heart. Okay, you guys ready to begin? You guys all seem thrilled. Okay, so let's start here. Oh, yeah, no, I want my markers. There we go. So the SA node. Why is the SA node the most important node in the body? It's a pacemaker. So it sets the what? Sets the pace of stuff, right? The pace is the same thing as what? You said it already. Heart rate, right? Oops. Yeah, Avery. So pacemaker cell is going to control the heart rate. Good. Pacemaker, the SA node, helps contract or depolarize what parts of the heart? What are the top parts of the heart called? The atriums. So it's helping depolarize the atriums. Boom, boom. Okay. Is this important? Atriums firing, is that important? What do you guys think? Probably, because what do the atriums do? What do the ventricles? Good. What do the ventricles do? What do the ventricles do? The rest of the body, right? Either to the lungs, if you're on the right, or the rest of the body on the left. Good. I want you guys to know this because this works in conjunction. If, for some reason, I'm getting no firing of the heart, right? What could be a problem? Probably SA node's not working correctly, right? If I only get the SA node working and no AV node action, the AV node is not working. Does that make sense? So look at an echocardiogram, we'll talk about in a little bit, right? You can see which node is not working. Now, which part of the heart is more important, atriums or ventricles? The ventricles. Why? Pumps blood to your body. What's the most important organ in the body? The brain. This controls you. So if this don't get blood, what happens? You're dead, right? So you always want blood to go to the brain, correct? So we always want our ventricles to pop and keep going. Good. So the SA node, we'll talk to this guy right here called the AV node. That AV node then takes electrical signal, moves it down this bundle of His, which is just basically a bunch of nerves, and it wraps around the entire ventricles through Purkinje fibers. Now, why are Purkinje fibers important in the ventricles? Makes contractions even, and it maximizes the contractions. The entire heart, entire ventricles contract all at one time and shoots blood out. Not at one time, but they can squeeze as much as possible. Does that make sense? Okay, that's important because do you want your heart to be not as effective as it is? You want your heart to be not as effective? You want your heart to be as effective as possible, right? So you want your heart to be as effective as possible, which means all the blood that's in your ventricles, you want it out. Does that make sense? Now, it doesn't work like that. Some blood will get pulled behind. That's fine. That's a bit normal. If too much blood is left over, that's when problems start to occur. That makes sense? Okay. This is just a conduction system. The first part is the conduction system. AV node, right? Sorry, no, SA node, AV node, bundled His, Purkinje fibers, contraction occurs, basically, right? It always starts with the pacemaker SA node. So let's talk about it. Let's talk about this graph right here. This graph is a lot of you guys' bane of existence right now. This is for all heart muscle cells, so cardiomyocytes, right? So normally, resting membrane potential. You guys learned that from 201 and 202, right? What enters the cell during depolarization? So what happens to the amount of sodium that goes in? That goes in, that's normal, it goes back up. Good. Once it reaches its peak, what starts leaving the cell? Potassium. The only difference between this and all of the muscles and nerves is we got this little tiny weird looking current thing right here, right? The reason this occurs is because as potassium's leaving, calcium kind of gets sprinkled in. Oh, Salt Bay, that guy, imagine him sprinkling some salt right there. That prolongs the period between hearts firing. Why do you want that to happen? Why do you want to prolong the heart so it's not always firing every 3 seconds? So we can relax. So we can have time to relax, right? Because the heart is always beating. It needs some time to relax, but it also allows itself to fill back up, right? So it contracts and then it relaxes. As relaxing, it fills up. And it contracts and then relaxes, it fills up, and it contracts again, right? Does that make sense? If it was normal, remember what a muscle and neuron looks like. It goes up, it fires, it goes straight back down, it fires, it goes straight back down, right? There is no moment to rest, which is good for neurons and muscles, right? But this is pumping blood. We want it to be as effective as possible, so we want to have as much blood as possible in the ventricles before it fires. That's the purpose of 2. And that is because of calcium. Does that make sense? So the heart is very, very, very sensitive to calcium because of this reason. Now, if I was in a hypercalcemic state or had hypercalcemia and have too much calcium in my blood, what would happen to my heart rate? Go up or down? No, heart rate goes down. You have more calcium, right? Which means this number 2 period stays longer. Does that make sense? So my heart rate goes down because my heart is going to rest until the amount of calcium goes down. That kind of makes some sense? Okay. So hypercalcemia is going to affect hypercalcemia, so calcium, not potassium, is going to affect heart rate. So if you don't have enough calcium, what happens to your heart rate? It increases. Good. This is why bone stuff is kind of important right now. Going back to osteoclast, osteoblast, stuff like that. Good, good, good. This making sense to you guys?
Yeah.
Anna, got any groups to you right now? Any questions in your group?
No, we're good.
Okay. Okay, moving on. I guess not moving on. There we go. Steroid calcium. Yep, yep, yep. Here we go. Same thing. This actually could be a test question. So I'm going to stop for a second and kind of go over this. So from 2 to 3, that is considered the absolute refractory period. What does that mean? What is absolute refractory period? What is that?
When you can't do another action potential at all.
Yeah, there's no action potential can occur, right? So when the heart is resting and refilling, it cannot beat again. Does that make sense? Because it's refilling. Good. Relative refractory period. If given enough stimulus, your heart can fire immediately afterwards, right? So if you're running for your life, you're exercising, if something happens, you can fire at 3 again. But this entire period of 2 is the heart's time to rest and refill. Cool. And then basically just down here, number 8 tells us the purpose, and that is basically just to rest and refill. Haha, it says it again. This stuff you guys remember from 201 or 210, right? That potassium is king on the inside. It's king on the inside. So where is potassium found? On the inside. That's how I always remember it, right? So potassium, always put king, potassium's on the inside, and it wants to leave. Potassium, calcium, chlorine, all that stuff's found on the outside, and it wants in. Okay. So besides heart muscle cells, what do you think is the most other important type of action potential to know? Probably the pacemaker, because that sets the pace of the heart, right? If this is going to beat, that's going to make our heart beat. So if the pacemaker depolarizes, will you have a heartbeat? Yes, unless something is seriously wrong with the patient. So let's talk about this. Back to red, because red is the most important color. So resting membrane potentials around -60. And right here, before we hit the threshold, what ion is entering? What do you guys think? Sodium. Good. Now here's where things are a bit different. As soon as we reach threshold, sodium plays no more role anymore. It is calcium. Now, what's the difference between calcium and sodium? Calcium's a 2+, sodium's a 1+. So which one's more positive? Calcium, by how much? 1, so it's pretty much double the charge, right? Which means this happens way quicker. Do we want our SA node to fire pretty quickly? Makes sense why we'd use the quicker model over the weaker model, right? So boom, calcium rushes in. We fire very quickly. And then, like normal, potassium channels open up. Calcium starts going down, potassium starts entering, and then we get to this part right down here. We overshoot, and then we go back to sodium. This is the funny current, right? The reason it's kind of like a funny current is it immediately goes from firing to slowing down to firing to slowing down, right? There is no really moment of rest. As soon as you're done firing and it goes down here, it's going to start going back immediately again. I don't remember why they call it the funny current. The only reason I could think of is because it uses sodium here and calcium up here, and that confuses you guys on tests, and that's funny because you guys get it wrong. It's the only thing I could think of. But this right here is the funny current, right? It's different than everything else. There is no overshooting. There is nothing. It goes exactly back to threat. It goes back to resting potential and starts going up again. And this is a constant thing. That makes sense. So, for pacemaker cells, what ion is the most important ion in pacemaker cells then?
Calcium.
Calcium, because calcium's that make it fire, right? Sodium just brings it up the threshold. Good, good, good. So the funny current is this thing right here, right? And that's just basically where we have slow depolarization occurs, right? It's slow, right? Everyone on a roller coaster before? How it slowly kind of goes up, and then as soon as then it goes really quickly up and goes back down, right? This is the slow going up part until you pass threshold, and then you shoot up like a bullet, and then come back down. Calcium and sodium. That's the only thing that's the only thing I would think to get test you guys on right now is calcium and sodium. Okay. Anyone have any questions on that? No, that makes sense? Okay. Cool, cool. Nice. Weird channels. So, let's look at the difference. Gap junctions link all cardiomuscle cells together. Hey, what are gap junctions? What do they do? Transfer ions. So when one part of the heart fires, guess what? All other muscle cells in the heart will fire at once, right? It goes boom, 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 boom. Does that make sense? Because do you want a part of your heart not firing? No, you want all your heart to fire when it needs to fire, correct? So heart cells talk to each other through gap junctions, right? So even a little bit of a thing can cause the heart to fire. That makes sense? So it's an all or none principle. Nice. So the heart is autorhythmic. What's that mean? Excites itself. Do you think about your heartbeat? Can you control your heartbeat with yourself by thinking about it? Yes or no? No, not really. I mean, you can hold your breath. You can give yourself anxiety, yeah, I guess, right? But that's just you thinking. But you only cannot control your heartbeat too much. Okay. I mean, there are ways to control it, but you can't control it for too long. And absolute refractory period is much longer in the heart. That it gives it some more time to rest and fill up. Okay. Now let's talk about ECGs or EKGs, depending on who your teacher is. If they're foreign, they'll say this. If they're native, if they're from America, they'll say that. It's just how they pronounce this. Basically what it stands for, electrical myocardiogram. So technically these people are most correct because it is a cardiogram, not a whatever K stands for. But basically this is when you get a patient, you put a bunch of stickers on them and you measure the heart. Congrats. This is very weird to do to a person. Because guess what? If you got a hairy patient, guess what they do to them? Got to shave their chest. That's fun to do. If you have a female patient, that's also annoying if they're well endowed too, because you have to put it underneath their breasts. I never liked doing these to patients when I did some stuff at hospitals. They're always weird. So, don't like this picture. I like this picture right here. So, whoa, that's making it bigger. I guess that's okay. So let's talk about the P wave. What does the P wave indicate? Atrial's doing what? Atrial's contracting, right? That's the first step, right? So the first thing we switch to is the atrial's contracting. Great. Atriums contract. They squeeze all the blood. Then that goes where? Goes to the ventricles. Good. Does the atriums relax? Yes or no? The atriums don't relax and refill up with blood for the next heartbeat. The atriums, if they contract, you have to relax. And the EKG does pick this up. You just can't see it because it's called the U wave. You guys see teachers talk about the U wave at all or no? Then don't ignore them. Then I'm not going to talk about it then. If you have an awful teacher, they'll talk about the U wave. Okay. So the P wave is the atrials contracting. That pushes all the blood into the ventricles. After you pump all the blood to the ventricles, right? What's next? What else has to contract? Sorry, atrium pumps all the blood to the ventricles. Then what's the ventricles have to do? Contract. That's going to be a QRS wave. QRS, right? Boom, boom, boom. QRS waves are going off. Nice. QRS, good. And then after the ventricles contract, what do they have to do? Relax, which is going to be your T wave. Does that make sense? Yes or no? So, if you see an EKG, you see some P waves. What's that indicate a patient is having problems with? You see multiple P waves. The atriums. If something's going on with the QRS waves and T waves, what's that issue with? Ventricles. Guess what we're going to talk about right now? Arrhythmias. Arrhythmias are basically looking at heart. Something's wrong with the heart. Here we go. So, cardiac arrhythmias. Something's wrong with the heartbeat. We know that because the word a in Latin means without, and rhythm means what? Rhythm, like music, pace, right? Speed. So the heart is without rhythm. That's not good. Heart should be with rhythm. Okay. Looking at this one right here. Move you guys up here. There you go. What is wrong with this guy? He's missing this, and this, and this, and this. He's got a couple things going on right here, which I'm happy about, but like really concerned about the things I circled in red. What's he missing? So yeah, his ventricles aren't contracting most of the time. See that? Is that a problem? Yeah. Okay. So this is called a heart block because guess what the heart's not doing? It's getting blocked. Not good. If your heart was doing this, immediately see heart attention because this is going to kill you. Your ventricles don't pump blood, you're dead. Now, luckily, it looks like it kind of picked back up, but he's going to be experiencing severe, or he or she will be experiencing severe chest pain because he went a couple seconds without his heart beating. That's weird. Makes sense? Your body can feel that. Good. So heart block, the most common case of a heart block is something's wrong with the AV node. And I know that because what else is firing? The atriums are contracting, right? So the SA node has to fire. The pacemaker cells are firing, right? And it's keeping the same pace, right? P wave, P wave, P wave, P wave, P wave, right? Do you see that? It's still keeping its beat. The AV node is just not working for some reason. So that's not good. So we'd probably give the patient, probably want to fix that. See? Boom. AV nodes damaged. That's not good. Okay, so let's talk about this. If something's wrong with the P wave, what part of the heart am I talking about? The atriums. If something's going on with the QRS waves, what am I talking about? Ventricles. Which one's more dangerous? Ventricles. So you got these PACs, premature atrial contractions. What does premature mean? It is firing before it should. We'll talk about premature stuff later on when we talk about reproductive. Atrials are going on and contractions are occurring. So put those letters together and you get some PACs. What PACs look like is normal. Let me use a different color. Let's use purple because GCU. So normal, PQRS, T, PQRS, P, QRS, P, QRS, P, P, QRS, P, P, QRS, P, right? Do you see those little, they're happening pretty quickly? Oh, I messed up. Wrong one. Ignore that drawing down there. Sorry. You have your P, QRS, PP, QRS, PP, right? Right here's the normal problem. You got two P waves together. So atrials are firing before they should. Now, is that going to kill you? Your atrium's firing too quickly. Yes or no? What do you guys think? No. This happens to every one of us almost every single day. You guys ever get surprised by someone? You guys ever, partake in caffeine and or stress? Or you see a very attractive person who talks to you, like your crush, your heart starts kind of skipping a beat, that type of stuff? That's a PAC. That's fine. These are kind of normal to have in various degrees. Now, if your heart is constantly doing these PACs, right? Probably not a good thing, right? But every once in a while, it's okay. Not bad. It's not the end of the world. Okay. So what's going on here is sometimes PACs can lead to PATs, which is basically atrial tachycardia. What's tachycardia mean? High heart rate. So I told you guys before, when the SA node fires, what happens to the heart? If the pacemaker cell fires, what's the heart going to do? It's going to fire, right? Because it sets the pace. Well, this person's atriums, this person's SA nodes an eager beaver, and it keeps on firing pretty quickly, right? So if you notice something, hello. Okay. Hopefully it's the wrong classroom. Hopefully there's no other classrooms in here. Shouldn't be. It's past 6 o'clock. Report said nothing, so we'll find out. Get kicked out. We'll just move classrooms real quick. Okay. So what's going on here is the atriums are firing, atrium's firing, atrium's firing, atrium's firing. What wave are we missing? Huh? T wave. Ooh, that's not good, is it? Means the atriums are not fully contracting, right? So not the worst thing in the world, because what are we still getting? We're still getting some QRS waves, right? That are still pumping out blood. It's just not as efficiently as possible. That makes sense? So not the worst thing in the world to occur, but yeah. So these usually occur because, like I said, you get stressed for too long, something happens, right? It also could occur because this happened. The heart skipped a beat. Is that normal? So the heart skipped a beat right here, and it's freaking out because it messed up. So it's trying to readjust itself, and it freaks out for a bit. Does that make sense? You guys have done this before. You guys start panicking about something, you mess up, and then you start panicking about the things you mess up, and you start acting up. You start doing a lot of things real quickly to try fixing the initial mistake, and it's not working because you're not allowing the things to just take a breath and fix everything at once, right? Welcome to your heart. It's the same thing. Okay. The heart basically is a caffeinated college student. It's stressed about everything and it always needs to keep going. Okay. Atrial fibrillation. So the atriums are fibrillating, which means they are fluttering like a butterfly. This is kind of bad. So this can get the heart going pretty quickly. All right. Look at this. We got a P wave, a P wave, a P wave. Got a T wave, a P wave, a P wave, a P wave, T wave, P, P, P. So these, basically your atriums are kind of quivering a little bit. They're not effectively firing. Is that a good thing or bad thing? Probably not a good thing, right? So the atriums are firing too quickly, and the what's going to happen here is your ventricles are trying to keep up, but they can't keep up, right? Because they have to rest and fire, rest and fire. So basically your atrium's firing about 500 beats per minute. That ain't good, right? That's pretty fast. That would kill you if it was what it really was doing, right? We don't take the heartbeat of the atriums, we take the heartbeat of the QRS wave, the ventricles. So that's not going to be good. However, this isn't as deadly as other things we're going to talk about, but it's pretty bad if it continues for a long period of time. Right? Because what's still beating? Heart's still getting some blood out, right? Some blood is still good to get. Okay. So besides shocking the heart, getting the heart back in rhythm, what are some ways to fix this? Huh? Well, lowering caffeine, yes, that would lower your heart rate. Good. But remember, the atrium, the valves of the atrium. So what valves control the atrium? What valves lead from the atrium to the ventricles? Bicuspid and tricuspid, right? They're not functioning properly. They're opening and closing really quickly, right? How would I quickly increase the amount of blood leaving the atriums into the ventricles? What do I do with the blood? What I theoretically would do to the blood? Could I theoretically thin the blood out, give you some blood thinners, make more blood kind of leave in that same amount of time, right? Because like thick blood has a hard time going through fast moving things, right? If the blood is thinner, it could run through easier. Does that make sense? So I theoretically give you some blood thinners. Now blood thinners don't theoretically make the blood thinner. They just either add more water or they get rid of some plasma proteins to make the blood more liquidy to move it through quicker. That makes sense to you guys? Cool. My favorite ones are coming up though, because these are stuff that kills people. So premature ventricular contractions. Woohoo. So let's see what we got a P, Q, R, S, T, Q, R, S, P. Is that normal? This guy right here, is that normal? P, Q, R, S, T, Q, R, S, P, Q, R, S, T, P, Q, R, S, T. Is that normal? Nah, the ventricles just fired out right after contracting. Did they get any blood? No, it didn't. They fired and fired immediately afterwards. Not good, right? However, right, it says right here, single PVCs, premature ventricular contractions, are common and not dangerous. You would feel kind of a weird like sensation in your heart and like, okay, that's over with. You usually see this in older patients. They kind of grab their heart for chest for a second, some chest pains, but it goes away pretty quickly. Probably see this if you spend some time with your elderly patient, your elderly family members. However, PVCs can increase by factors of, I don't know, epinephrine. What's epinephrine do to the heart? Increase heart rate, right? So is that higher chance of the heart's like firing to be quicker than it should? Yeah, good. Drugs. What type of drugs could increase my heart rate?
Nicotine.
Nicotine, all type of uppers, right? Those fun ones, good. The ones you guys should not be taking this week of exams, don't do that. That's bad. Man, I know it goes on the. Hey, I mean, college students do college students. I hear rumors. I know things happen. I get emails about what gets complicated from rooms. So also, if ion changes occur, right? So if less calcium's in the heart, more likely to fire, right? If I have way too much sodium in the heart, right? I can fire quicker. Less potassium than normal, I can fire quicker. That makes sense. Cool. So one PVC, not important, but could be a concern. VT, ventricular tachycardia. This is multiple PVCs in a row. So, yeah, that doesn't look good. Is this person pumping blood? No. You only pump blood when a QRS comes after a P wave. I see one P wave. That's not good. So the heart is not effectively pumping blood. And what else is it doing? It's just wasting energy, right? It's wasting ATP. Bad, serious problem. Not may, it does indicate a serious problem. Good. And then lastly, VFib. This is the most dangerous out of them all. Because look at this thing. It's not even a heart, it's not even an EKG, it's not even a heartbeat. So, who here watches like Grey's Anatomy and all those soap opera medical shows? You know when the heart goes beep and it flatlines? Yeah, you don't waste paddles on that person. That person's dead. Heart's not beating whatsoever. Only time you want to shock a patient and like do epinephrine like really dangerously is during VFib, because their heart ain't beeping at all, right? So you want to try shocking the heart. When you shock the heart, what it does actually, it stops the heart. And you're trying to reset it. Make sense? Because right now what's going on is not even, it could be the AV node messing up, or it could be SA node or AV node messing up, while the entire Purkinje fibers are freaking out. So shocking the heart stops it for it to restart. Does that make sense? Okay. Not good. Okay, and we got any questions on arrhythmias?
Can I ask you a question real quick?
Sure.
It's not about like anatomy real quick. It's just one quick question. Is
Okay.
the Chem 115 exam this Friday, or like this week or next week?
From what I've heard, it was this week, though they're thinking about moving it to next week, but I don't know. Talk to your professor. I'm just your lab professor, guys. I don't control anything with lecture.
Okay, thank you.
Yep. I have no powers. I'm the lowest person on the totem pole. Ooh, long QT syndrome. This sounds scary. So what's long? QT. What that means from R to R is pretty long, which means the heart rate is a long time. All right, if I can get rid of this. Boom. So what do you guys see the difference between normal and abnormal? What's the difference? That T wave looks normal. Is that T wave being that huge hump normal? No. So what's going on is the ventricles are not repolarizing or relaxing enough, which means they're not being full up, they're not being filled fast enough. Which means what? Is your heart beating effectively? No. So this is a syndrome. So do you think people can inherit this thing genetically? It's called a syndrome, so probably, right? Now this is not going to be deadly. Just means your heart's not going to be beating effectively. Could lead to issues, could indicate issues. It all depends on the patient. So you can also look at EKGs. You can notice some things. If the QRS waves, so Q, R, what am I doing? I have a freaking thing right here. And S and T wave. If those are above P, you have elevation occurring. This means part of your heart is dead. You had a myocardia infarction, which basically is just a fancy way of saying you had a heart attack. All right? You had a heart attack, part of your heart is dead, so it's not beating effectively. Does that make sense? If your Q, R, S, meaning your S and T wave, if those are below the P wave, you have a depression, ST depression. right? What can give you, you can have ischemia, which just means you're having blood clotting your coronary arteries. What's the coronary artery do?
Doesn't it pump blood to the brain?
No. Coronary arteries supply the blood to the heart. So if that's getting plaqued up, is that a good thing? What are you asking for if that continues? For a total blockage of the coronary artery, which is going to cause what? Stroke or heart attack, right? Bad, right? So depressive one basically means reduced blood flow, probably due to plaque buildup, right? Which is going to lead to an elevation when they get a heart attack. Does that make sense? So this means they already have a heart attack, and this means they are going to get one soon, if not fixed. Kind of make some sense? Cool. Hyper. So, calcemia. So what's hypo mean? Hyper. Low. Hypo mean low. Hyper mean high. Good. What's the K for? Potassium. So hypocalcemia, I can't say it correctly because of my accent, but kalemia, right? For hypo, what's going to happen is you're going to have this prolonged U wave. What's U wave? I told you guys already. The U wave is going to basically be the atriums are going to repolarize. It's them relaxing, right? But you guys don't need to know that. Basically, just know T wave gets pushed down. So, potassium found inside or outside? So where's it go? It'll go outside the cell. This is going to help us cause depolarization, right? When potassium leaves, depolarization occurs. That makes sense? So if I don't have a lot of potassium inside my cells, right? That means that takes longer to occur. Make sense? So P waves and T waves kind of take longer to happen. The heart takes longer to repolarize than depolarize. That makes sense? Yes or no? Okay. So when you have hypercalcemia like here, you have elevated T waves. They're freaking crazy peaky, right? What's going on here is that you're repolarizing very quickly. Would you want to walk up a steep hill right here? Yes or no? No. So that's not good. Why is that not good? What's the ventricles not doing? They're not repolarizing quick. They're not repolarizing their normal speed, right? So they're not pulling back, refilling so they can fire again, right? Make sense? They're quickly, I'm good, fire, I'm good, fire, right? So this is why you can kill patients if you give them potassium. Probably heard of like those serial killer nurses that go around and kill patients, right? They kill patients by injecting with too much potassium. This is what they can do to you. This is how they kill you. Now you guys know, and this is being recorded. I'm not held liable for anything I teach my students. Okay. A lot of words. I like the red ones though. So, systole basically just means contraction. So if I start saying systole again, just know it means contraction. If I say diastole, it means relaxation. That makes sense? Cool. If you need a way to memorize this, if your heart don't beat, what happens to you? You die. So dying, or diastole, is when your heart's not beating. Boom. That's how I do it, at least. If it sticks to you, it sticks to you. If it doesn't, find some other way. Okay. Oh, great. What's this? So this is how our heart beats. You guys just don't think about it as much, right? So, first stage is ventricle filling. So, During diastole, right, blood is let into the heart, it's let into the atriums, right? And then that is allowed to pull inside of the ventricles. That makes sense. Okay. Then the atriums systole or contract. They pump all the blood they can into the ventricles, right? Then what happens is your valves, tricuspid and bicuspid. Hello. Tricuspid and bicuspid try pumping the blood out. Now, that's normal, right? Good. Okay. Then blood, sorry, this is called isovolumetric because the volume here equals volume here, basically. Volume here equals volume here. So the valves can't let blood go back through, right? Your bicuspid and tricuspid valve basically stops regurgitation from occurring, right? Because you don't want blood from your ventricles to shoot back up into your atriums, correct? Is it efficient if it happens? No. Heart's inefficient. What can happen to you? You can die. Pretty much. Anything with any heart condition basically means you can die. Okay. Then we have ventricle ejaculation or ejection. I misspoke. Wow, I'm already in reproductive. Ventricular ejection. Yeah, I know. That's going to be a fun time in reproductive. I was helping my sister who's already on reproductive somehow in high school, and that was weird. Having that talk with my sister. So that's fun. Okay. So ventricular ejection is shooting the blood out. I mean, it means the same thing both ways, guys. It's funny, yes, but it actually means the same thing. Something's getting shot out somewhere. Okay. Boom. Being ejected out. Afterwards, equal volume, blood starts pulling back in, and yay, we're all good. Does that make sense? This is how the heart normally works. We just don't think about it like this in the roundabout way it happens. Yeah, it's fine. I've said organism and orgasm before in front of people before. I don't care. The worst thing part is going to go on YouTube, so when they see that, that's going to be great. I can't remove that part, so. Okay. If this picture right here is confusing to you, well, guess what? We got a circular picture that's even more confusing. I don't like the circular picture. If you do, great. Basically means when the ventricles are not firing, guess what does fire? Your atriums. When your atriums are not firing, your ventricles can fire. And there's a long period, about probably half this graph is nothing firing. So your heart can fill back up, basically. Does that make sense? Yeah. Okay. I don't like the circle graph. Woohoo! We talked about the heart for a while. Nice. Now we're going to talk about murmurs. So, you guys have probably heard about the lub-dub, right? Lub, dub, the heart goes makes a lub, dub sound. So what actually makes the sounds is the valves opening and closing. That's what makes the sounds. You can kind of hear, if you're if you have very good hearing or you know what you're looking for, you can hear the contractings of the atriums and blood flowing to the ventricles, right? Though usually found in older patients to hear for this. But if you're good enough, you probably can hear it. So I talk about the lub-dub sound we're going to talk about. Move it back up here. So the lub sound, right, occurs when the basically, blah, blah, blah. My marker back up, erase that. So lub sound, S1, is going to occur when the basically AV node fires and the tricuspid and bicuspid valves close. The dub sound happens when the aortic and pulmonary valves open up. Good. So normal should only hear sounds about here and about here. Does that make sense? I only care about 1 and 2 right now. So between 1 and 2 firing, I hear all this kind of sound going on, like gurgle right here, right? Means you have stenosis of the aortic valve. That's not good, right? You hear a little bit of the gurgle sound going off. That's mitral regurgitation. That means blood's being pushed back up into your atrium. If you hear gurgling sounds after the dub sound, blood is being put back into your ventricles because it didn't get pumped out of your aortic or your vena cava. Or, sorry, yeah, aortic or your pulmonary artery or aortic artery. My bad. And then if you hear this weird gurgle sound the entire way through, the patient has a ductus arteriosus. The patient has a ductus arteriosus, they're probably not going to get that fixed. So what ductus arteriosus does basically is when your blood vessels are connected to each other. This mainly occurs in fetuses, right? Does it kind of make sense? Do babies breathe? Do fetuses breathe? No, right? But they get oxygen from your mom, right? They pull it because of gamma hemoglobin, right? So they get oxygen. So they have oxygenated blood, right? But they don't need to breathe, so they bypass the entire part of the lungs, right? Because they're not using it yet, and they pump blood around. When the baby gets pulled out or cut out or happens to a vaginal birth of baby, they get exposed to oxygen for the first time. That pressure, they breathe it in, right? When they're crying, pops their lungs open, it closes this arteriosus, and their heart should beat normally, right? That's why you want a baby to start crying when they're born. Well, doctor's kind of slap it and make sure it breathes. It's not because it's fun. To make it breathe. You want the baby to take a gasp of air that pops the lungs open. Does that make sense? Good. If the patient has this and they're not dead, it probably isn't that big of a deal. Okay, cardiac output. This basically just means how much the heart is outputting, right? That is controlled by the heart rate and the stroke volume. So let's save us some time. What's the heart rate? What's the heart rate? The rate at which the heart is beating. So the heart rate is just the rate at which the heart is beating, right? High heart rate, tachycardia. Low heart rate, brachycardia, right? Good. Stroke volume is a bit more different. We'll talk about that in a little bit. I'm going to quickly go over heart rate because that concept should make sense to you guys. Good. Let's talk about cardiac reserve though. So this basically just means all of you guys right now are sitting down. Should your heart be freaking out and pumping as hard as it can right now? Yes or no? No. This is your resting heartbeat, right? Resting cardio output. Does that make sense? If you get up, start exercising, your heart's going to beat faster to compensate for that, correct? Good. If I take an obese patient, 500-pound person, and make him walk on a treadmill going about 5 miles per hour, his heart's going to be beating pretty quickly, right? Even though it's a menial task, right? If I take Usain Bolt, who's a sprinter, pretty healthy, fit dude, right? I put him and make him walk on the same treadmill, the same speed, his heart's not going to even care about what he's doing because he's such in good shape. Does that make sense? So basically, cardiac reserve is how much energy you can save by doing nothing. Does that make sense? Okay. If you're healthy and you have more reserve, you can save your energy for when you need it. If you're unhealthy, your heart's always working 100%. That's why unhealthy people tend to have heart attacks faster. Okay. Heart rate, tachycardia, brachycardia, and pulse. Okay. Chronotropic or chronotropy. Chrono meaning time in Latin, right? Tropy just means measurement. So I'm measuring something in time, which just basically means I'm measuring heart rate. So if something has a positive effect on heart rate, it's positive chronotropic, it's going to increase heart rate. Something has a negative chronotropic thing, it's going to decrease heart rate. Does that make sense? Cool. Going flashbacks to 201 and to 210. Sympathetic, fight or flight. Fight or flight, right? Good. Parasympathetic. Rest and digest, R&R. Good. So if your sympathetic functions are firing, what happens to your heart rate? Parasympathetic wins out. What happens? Decreases. Next couple slides basically just say just that. If you're in a sympathetic state, your heart's going to fire. If you're in parasympathetic state, your heart's going to slow down. Woohoo, action potentials happen again. Woohoo. Yeah. So, atropine. What? Atropine. What does atropine, guys? Remember, you guys remember what atropine does? What's atropine do? You usually put those in your eyes get really big, right? It's going to block muscarinic receptors or basically just block parasympathetic function. So I take a vial of atropine and I just inject it in my heart, right? I block all parasympathetic function. What wins out now? Sympathetic. So is my heart going to go really high or really low? It's going to go super high. And there is no brakes now. It's like you're basically flooring your heart. You're pressing on the gas as much as possible. Now, this is fine if the person has no heartbeat. You can kind of inject them with some atropine, A-okay. If I just walk up to a random person and just inject them with a ton of atropine, I just killed the person. Heart's gonna beat so quickly, they're gonna have a heart attack, basically. That make sense? Yeah. Other things that can affect it. If I have a burst of epinephrine or norepinephrine, or just take epinephrine or norepinephrine, catecholamines, right? Bumps up heartbeat. If I take caffeine, also increase heart rate, right? Because it's going to stop the breakdown of these guys occurring. Nicotine releases catecholamines. So you see how these drugs basically that are uppers, caffeine, nicotine, basically just help the body do what it normally does anyway. That makes sense? Cool. Hormones. Oh no. They do stuff. Talk about some hormones in a little bit. Okay. Now talk about stroke volume. So stroke volume basically is your preload and your afterload. So what does pre mean? Before. And load just means amount of something, right? So preload is how much stuff is entering the ventricles. So do I want a high preload or low preload? I want a really high preload, right? I want as much blood as possible entering my ventricles so that I could pump all that blood out. Does that make sense? Okay. We'll talk about this in a little bit. Exercising. Yeah. So healthy people, heart's more efficient. That should just make sense, right? So if you increase your exercise, you're going to increase your preloads. That's why you're supposed to kind of warm up a little bit before you start doing major exercising. Stretching, maybe doing a quick jumping jacks, quick jog. Will increase exercise, will increase your amount of preload. Good. So talk about Frank Stirring's law of the heart. So what this basically means is the heart is elastic. Right? I take a rubber band and I pull it apart, let go, what happens to the heart? Comes back and closes, right? Same thing. If I take a bunch of blood and I shove it into my ventricles, it's going to push the ventricles, right? And that rebound effect is going to push all the blood out, hopefully, right? So an increase in preload should decrease my afterload, right? I should get less blood afterwards. That kind of makes some sense? So heart's like a rubber band. Now, this right here, it has some limits, like a rubber band. If I take a rubber band and keep on stretching it, well, if I stretch it too much, it breaks. Heart, same way. If I put too much stuff into it, it's going to burst. This isn't, it's not gonna, it helps a little bit, but it only helps. How it works conceptually is you have your actin and myosin, right? You guys remember this from class? Boom, boom, boom. This right here, they're too close together. They can't overlap anymore, right? So that's not going to cause a lot of contractions. So you push them away a little bit. You're going to look better, right? You're increasing the sarcomere length. That's normal. However, boom, Goldilocks zone, where they have a lot of room to overlap. So tons of contractions can occur. Over here, yeah, they're not overlapping anymore. They can't contract. That's bad. Gonna make some sense? Kind of pull things back in from last semester. So, things that will help contractility, basically the contraction of a heart. Hypercalcemia, right? Tons of sugar, catecholamines, those will help. Factors that will not help the heart. Hypercalcemia, hypocalcemia. That kind of makes some sense? Hello. We're kind of going to skip the ionic thing right here. The reason being is because I don't think you guys need to know about this stuff. Did you just talk about this at all or no? I didn't think so. It's weird. It's a weird thing. Basically, just the ions, either calcium or potassium or calcium, the amount you have, will affect the conductivity of your heart, which means how much you can contract or not. That's what this slide's trying to say right here. Afterload. How much blood is left in the heart? Does that make sense? Do I want a high afterload or low afterload? I want a low afterload. If my afterload is higher than my preload, that shouldn't be possible, right? Because basically, I have more blood in my heart than I let in before. Something seriously wrong if the stroke volume is negative, right? But if your stroke volume is small, it means you have a heart condition, probably really bad, such as lungs are not working properly, so blood is being backtracked into the lungs, right? Because the lungs can't give up the blood oxygen, they can't push it out and let more blood in, right? There's probably some blockage at the lungs. You could have some sclerosis of the veins. This will cause hypertension or hypertrophy. Myocardium, so pressure in the heart, which is bad. You don't want the heart, anything wrong with your heart. Okay, I don't, well, we keep using this guy right here. He's creepy looking. I don't like him. Blah, 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 blah. Ah, Fat Mario. I don't like Fat Mario either. If you exercise, your heart works better overall. That's why you always tell your patients to do what when you see them? To exercise. You go see your doctor, they always tell you to exercise. It's because any amount of exercise is going to increase your heart. It's going to make your heart work better. Increases heart rate, increases cardio output, increases your stroke volume. That makes sense? Exercise is good. Exercise is good. Always exercise. Oh no. Unbalanced. Left heart failure. What's your left heart do? What's your left heart pump to? What's your left heart pump to? Huh?
Systematic.
What?
It pumps to the systematic circulation. I mean, not to the systematic circulation, to the pulmonary.
So what's it pump to, guys? Pumps to the lungs. Hint, hint. That's why there's a picture of the lungs up there, right? So left side of the heart's going to pump to the lungs. What's the right side of the heart pump to? The body. So if you can't pump with your left side because there's a problem with your lungs, that's going to backtrack your blood. Am I saying something wrong? Is it the opposite? Oh, forget this out real quick. Maybe I'm a brain fart. Right side of the heart pumps, receives oxygenated blood from your veins and pumps to your lungs, where it picks up. The left side of your body receives oxygen-rich blood, pumps to the right side of your body. Ah, so that's the left side pump receives it. Okay. Left side of your heart receives oxygen-rich blood from your lungs and pumps it throughout your arteries to your body. Okay. Darius, you're wrong. Sorry about that. I was wrong too. It's all good.
My teacher confused me, that's why.
Huh?
My teacher confused me. Like, we keep doing cahoots. I get it wrong every time. I don't know.
Okay, left is going to address the body, right's the heart. So, basically, if your right side fails, your left side's also going to fail. Reason being, blood gets pumped. Let's use black. Blood gets pumped here, right? Yay, stuff happens and gets back here. Right side of the heart outseeds the left side, right? What's going on? If this side of the heart right here, right side, not going to beat. Left sides can't pump blood. That's not good, right? You need your right and left side to pump blood. If one side breaks, the other side's also going to break. Does that make sense? Okay. What occurs here with left side heart failure is blood's going to start pooling in your lungs. Do you want fluid in your lungs? Probably not. What should be in your lungs? Oxygen and a little bit of that. Okay, so people with big hearts, sorry to tell you this, you're gonna die. Bigger hearts are bad. There's a reason for this. Why do you guys think bigger hearts are bad? Less volume to the lungs, but also, it's kind of a weird way of thinking about it. But let's look at some beefy men. Beefy men. Beefy men. Beefy men. You'll see why. Cool. These guys are ripped. That's nice. Look. Oh no, this guy's even. No, this guy's worse. Right here. This dude. Small head. I can make fun of him. It's fine. He lives in Arizona. If he finds me, it's fine. If this dude were to flex his biceps outrageously enough, but if you flex your biceps enough, you have too big of biceps, you can't touch your face. Kind of makes sense? His muscle will be too big to do that, correct? Same thing with the heart. The heart gets too big. It can't contract fully. Does that make sense? Because the heart muscle gets in the way of itself contracting. Does that make sense? That's why these world's strongest men and stuff like that, they have a hard time living because you're not supposed to be that gigantic. Yeah. Cool. Hitting edema. This is a good case of right heart side failure. So if I poke you and my finger and the indent lasts for a bit, that probably isn't normal, right? Because you get too much fluid pulling in places, kind of like your body, because blood isn't going into your right side of your heart, pumping into your lungs, you put it to the left side. Does that make sense? There's probably some blockage leading up to the right side of the heart. All right, let's talk about all this stuff. Fun. This is the next stuff right here. Blood flow. I'm skipping some stuff because it should be a little bit common sense. If it's not, come talk to me. I don't think you have to do any math in the exam. Did they mention math at all or no? Probably no math then. Don't worry about that. Viscosity. What does viscosity mean? How thick something is, right? So if your blood is super thick, is that a good thing? Probably not. You don't want your blood to be sludge, right? But do you want your blood to be too liquidy either? No, body wants a nice, happy medium, right? So if you have viscosity, most likely you have anemia. If your blood is too thick, you're most likely dehydrated. Makes sense? Because you don't have a lot of water in your blood to make it nice and loose, you're probably dehydrated. Turbulence, all right? So blood should only flow in one direction. Sometimes when you got some plaque in your heart, because you ate the double-doubles too many times, that causes when blood kind of comes, it kind of gets kind of swirly like a bunch of rocks in a river or a pond, right? That's going to cause the blood to kind of swirl around. That's going to reduce blood flow to places. Is that normal? Yeah, no. Turbulences are not good. It's cool to see. It's cool to see when you inject dye into someone and look underneath an X-ray. That's kind of cool. Yeah, what's up? So no, the veins in the legs are different. We'll talk about those in a little bit. I think we talk about valves in a little bit. What's going on? Did we talk about veins at all? Oh, those things? Yeah, where are those? Okay. Okay, it's in the first PowerPoint. Okay. So let's talk about it right now. Brought it up. So veins are different. Arteries to arterioles, right? They should just be, blood should just be flowing through nice and evenly, right? Veins are different. How do veins flow? They flow up to the heart, right? So what are they working against? Working against gravity, right? So if I have a bunch, if I have a vein, right, and I have some blood in it, let's make the blood, it's kind of blue, right? How do I stop all the blood from just going down because of gravity? What do I have? What do I have in there? I have valves, right? So I have all these valves in here. And that stops the blood from being pushed down. Does that kind of make some sense? So turbulence does not occur because blood isn't flowing in veins, it's being pushed up. So what causes this to happen? What causes the blood to get pushed up? What do you guys think? Skeletal muscles. So how do you move your skeletal muscles? You walk around. So you walking around and being active is how you move blood around. Does that make sense? So if I got a patient and all I do is sit around all day for 8 hours a day, are they moving around a lot? No. So blood is going to start pooling in these areas, right? What happens when blood becomes stagnant and pools for too long? It clots up, gets all coagulated, right? Kind of thick. Great. So if I get a patient, let's say they're on a flight for 12 hours, and they don't get up, they never get up to go to the bathroom or walk around, then they finally get up, that congealed blood is a clot, it opens up and starts moving, now it's an embolus, right? And it'll go to the heart, and hopefully it doesn't kill the person because it can block the heart up, or go to the brain or the lungs. That makes sense. What causes pulmonary embolisms, can cause a stroke in a person, that type of thing, right? A blockage somewhere. That's why it's always good to move around. Even if you're like a long car ride, after every 2 to 3 hours, you need to stop at a rest stop and get up and walk around because you don't want your blood to be pooling. Make sense? Okay, that's how veins work. Okay. You don't see too much turbulences. It usually occurs because of plaques. Cool. That makes sense, everyone? Cool. Yeah. So we go from arteries to what? Arterioles to veins. Which are the biggest ones? Arteries, and then what's second biggest? Veins. Third biggest? Arterioles, then venules, and smallest is capillaries. Why do we want? So we have the lowest pressure inside capillaries, right? Because they are the smallest, right? However, capillaries have the most surface area. Does that make sense? Do you want your capillaries to have the highest surface area? Why? So you can get your blood, all the oxygen, nutrients in your blood outside the blood to where they need to go. Your arteries really don't have a lot of surface area. All they're meant to do is pump blood. They're not supposed to absorb anything. That kind of makes sense? Cool. So this picture right here was confusing some students I talked about. Yeah. So where is blood pressure lowest in the body? Huh? The veins. Good. But veins where? Where do you get, if I walk outside right now, what's the first part of me that will get cold? The fingers or my toes. Why? And your nose. But your nose a little less. But why your fingers and your toes? That's the furthest away from my heart, right? Heart beats. That's the highest pressure is right there. As it goes away from the heart, pressure drops. That makes sense. That's why veins need to have valves too, because there's no force pushing blood through them, right? After you get to the veins, there's pretty much none whatsoever. Does that make sense? Capillaries have a little bit of pressure. That's good. I don't want to have too much pressure. Why? They can burst. Is a burst capillary a good capillary? No. I don't have to have too little. I don't have to have too little either, because why? Nothing's gonna go through, right? Cool. Capillaries also have the lowest blood flow, which makes sense, right? We want to slow things down, make sure things happen in the capillaries. Does that make sense? Cool. So, which one of the vessels, right? Arteries, arterioles, capillaries, venules, and veins can control blood pressure? Arterioles. Why? What's around them? Smooth muscle. Smooth muscle can do what? Muscle can either contract or relax. So if I muscle around, right, a venule and it contracts, what happens to it? Gets smaller, vasoconstriction, gets wider, vasodilation. That's where that stuff occurs. It's in the arterioles, not the venules, arterioles. That's where vasoconstriction, vasodilation occurs. That make sense? Seeing lots of blank faces. We've only been doing this for 2 hours. What's up? Why is it the lowest in papillaries? Because you're still got blood still going into them, right? So blood is still kind of pushing blood in and out, like out of them, right? So it's got some bit backup there, right? Afterwards, with the veins, it's going against gravity, and then blood at that point in time, there's no way blood can push it. That's why blood pressure is lowest there. Okay. We talked about that already. Okay. So you have two types of pressure, systolic and diastolic. So what do you think the systolic pressure is measuring? What? Contraction of what? The ventricles, right? Because, I mean, why would you say atrium? Why would I measure the contraction of atriums? Okay. I don't take the blood pressure of the heart. You just take blood pressure in a blood pressure cuff or the finger, right? So the systolic is how much blood is being pushed out, systolic, and diastolic how much blood is being kind of let back in. So normal is 120/80. Systolic over diastolic. If you're like 140/90, high blood pressure, probably not good. Don't know why we have a happy monkey saying the silent killer is high blood pressure. This guy scares me to this day. He's too happy about that. Okay. So arteries have this cool ability where they can expand real quick, kind of quickly, and kind of shoot blood out, right? Arteries have to do this because why? Because they deal with the highest pressure. So, for example, what's the arch right here called? Aortic arch, right? Blood is being thrown at this curve right here every day, right? Every couple seconds, right? That needs to be able to give some give and shoot blood down the arch, right? You don't, if it didn't have any give, eventually it would just burst. Make sense? So arteries have to have some give and take. They're kind of rubbery. What are not rubbery are veins. Veins are pretty thick because why? They have valves, right? So they can't be rubbery. Nice. Cool, cool. Blood pressuring cuffs. We've all used these before, right? Yes? No? I know you guys all at the store, you guys before COVID, you guys are young. Ever walk up to one of the machines, put your arms in and hit the button? You guys never did that before? So am I just that old? So before COVID, during like at the mall or at like the pharmacy, there was a place off in the corner that had a blood pressure cuff. You kind of sat down, put your arm in it, and read your blood pressure. You guys ever play with that as a kid? Yeah, at the mall. It's like right in front of like the health food store. Yeah. Do you guys ever do it as a kid? You're not supposed to. Why? What happens? It gets pretty tight in your arm when you're a kid, right? Well, one, because your arm's too small. But what goes on is it needs to, so it keeps squeezing and squeezing and squeezing and squeezing, right? Because it has to get up to about 120 pressure or higher. If your blood can kind of go through that, right? It means you have higher blood pressure in the cuff. Does that make sense? Yes or no? Okay. And usually we'll get a listening device and do that. This isn't as common nowadays because now new technology does it for us, the little fingerprint cuff. We got those ones that kind of the patients do on their own, the arm cuffs, right? Just be careful. If you do the arm cuff wrong, it gets really tight and it actually made my arm go purple once. Luckily, they built an off switch where they'd stop so it doesn't just crush my arm. That would have been bad. But yeah, that's how blood pressure cuffs work.
My partner did that to me in the lab.
That sucks, huh?
Yeah.
Mm-hmm. Yeah. Okay. So let's talk about some stuff. So baroreceptors, what are they measuring? What? Pressure from what? We're talking about the blood in the heart, right? So what are they kind of measuring? Required blood pressure. You have these carotid arteries and also the aortic arch. Why do you want them there? Where the carotid arteries go? The brain. Does this guy want good blood supply? Yeah, right? So if you don't get good blood supply, does he start freaking out? Yep. What can the brain release really quickly? Hormones, what the last exam was on, right? A lot of hormones start up here. So blood pressure needs to be monitored to the brain so it can quickly react to it. Aortic arch, because that's where all the blood kind of comes out from. So, is it a class or something? Who is it? Do you want to, someone go outside real quick and see if there's a bunch of people waiting outside? Okay. I mean, there shouldn't be any classes in here. There shouldn't be. It was on the board. Okay. Nice. Okay. If you have high blood pressure, how does your body fix it? Wait, hormones, yes. But before we even get to hormones, what's a quick, easy way of fixing things? Hormones take time. Quickest way, huh? Quicker way than that. So increased blood pressure, usually because of something, right? The answer I'm looking for, if you have high blood pressure, your blood vessels can vasodilate. That lowers pressure. Your heart rate can also slow down. Less blood is being pumped, right? There's less blood being in your system one time. That should decrease blood pressure. That makes sense? That's what your heart's gonna, that's what, if you detect low blood pressure, so your body's in, high blood pressure, your body's gonna do it pretty quickly, right? You have low blood pressure, vasoconstriction, increased heart rate, try to fix that problem. That kind of makes some sense? Cool. There's some chemo reflexers. What do chemo what do chemo do? What do they measure? Chemicals. Again, carotid artery. Why? Do you want some weird things going to your brain? Probably not. So they're going to measure these three things. Only ones you need to care about, though, are O2 and CO2. Reason being, pH is basically the same thing as CO2. CO2 is an acid. Carbon dioxide is an acid, right? So if you have more CO2, you have lower pH. That make sense? Okay. If you don't have enough O2 in your blood, is that a good thing or bad thing? So what's going to happen? What's your body going to do? If you hold your breath long enough, what are you going to do? You're going to get gasp air, right? That's a reflex. That is something you can't control. This is why drowning is the worst way to die, is you will eventually inhale water and then freak out. It's not a peaceful thing they show in the movies. It's awful. Good. If you have too much oxygen in your body, what's going to happen? You're going to slow your breathing down, all right? Kind of make some sense? And you can't have too much oxygen. When can you have too much oxygen in your body? Hyperventilation can occur, right? That's probably not a good thing when you're stressing out and freaking out. Good. Exact opposite CO2. Cool. Ba-da-ba-da-ba-da. Talks about it right there. Now we're talking about hormones. So this is how we control our blood via hormones. This is the renin, angiotensin, aldosterone pathway. Your instructors talk about this at all? Some say yes, some give me weird looks. Let's talk about it, because guess what? It comes up. Because guess what? It involves the kidneys, the liver, and the lungs. Guess when the next exam's over? Those. So this can come up on the next exam as well. Let's cover it. So if I'm dehydrated, what's that cause in my body? I have thick blood, right? But if I'm dehydrated, what happens to my blood pressure? Go up or down? Blood pressure
Down.
go down. If I have not enough salt or sodium in my blood, how much my blood pressure? Go up or down? What do you guys think? Goes down. If I have a hemorrhage, or if I bust my head open and start leaking tons of blood, how much my blood pressure?
Down.
Go. What do all those contribute to? All these things right here are causes of what? Low blood pressure. So basically, if you have low blood pressure, this is when you use the angiotensin, renin angiotensin cycle, right? Or RA pathway, basically. This is response to low blood pressure. First off, the kidneys. We haven't really learned about the kidneys yet. What do the kidneys do? They filter what? They have access to blood, right? They have a finger on the pulse, right? Hey, they sense low blood pressure, so they start releasing this thing called renin. That's why it's called the renal system, because of renin, right? Also in your blood, you also have this thing called angiotensinogen. It's produced by the liver. When renin angiotensinogen, there we go, I had a stroke right there. When they meet up, they form this thing called angiotensin 1. Congrats, angiotensin 1 doesn't do anything just yet. It needs to go to the lungs. Meet this thing called ACE. ACE is an enzyme. It converts angiotensin 1 to angiotensin 2. This is where we actually can start doing something. First off, angiotensin will cause the arterioles to vasoconstrict, which will do what to blood pressure? Good. How much time did I waste just to cause vasoconstriction? It was a lot of time, right? It's a lot of steps. Is that enough bang for my buck or no? So let's use more bang for my buck. Angiotensin 2 also goes to the adrenal cortex, and it will increase aldosterone. What layer of the adrenal cortex holds aldosterone? Salt, sugar, sex. So what layer? Zona fasciculata, the first outside layer. Can't forget this stuff, guys, because guess what happens up in the renal unit? The adrenal glands are there. It's a little hat on the kidneys. It's kind of important. So increased aldosterone. That's going to basically make you retain salt. If you retain salt in your system, what else do you retain? Water. If you retain water, what happens to blood volume? Blood volume goes up with the blood pressure. Boom. That's how you increase blood pressure with the angiotensin cycle. Does that make sense? How you hormonally control it? Yeah. It takes a long time, right? That's why we're going to do neural and or physiological stuff first, like vasoconstriction and decreased heart rate, or breathe to fix the other problems, right? This happens, and it's a long time to respond to this, but it will happen. Does that make sense? Okay. Now, I have a hormonal pathway that actually will increase blood pressure, and that is ANP. ANP is basically the only hormone you guys need to know that increases blood pressure. Not increase blood pressure, or decrease blood pressure. ANP is going to decrease blood pressure. It is the heart going, hey, 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 now give me a break, cool your horses, and reduces stress in the heart. Does that make sense? It's kind of important because does the heart want to work out fully the entire time? No, only when it needs to. Does that make sense? Okay. Yay. That is blood. Anyone have any questions on blood or the heart? Anna, Michael, Jason, Adarius. Any questions for me so far? Jason, if you're speaking, I can't hear you. 1 second, is my mic working?
Oh no, I don't have any yet.
Oh, okay, you're good. You're not muted. Okay, no questions?
Oh, no, I don't have questions. My professor told me everything I should know about blood, kind of.
Okay. Did I go over everything?
Yeah. Yeah.
Okay.
Or I missed the first half, so I don't know. But yeah.
Okay. So, lymphatic is going to deal with what, guys? Immune system, right? Going to deal with your lymphocytes, white blood cells. Let's talk about it. Before we do anything, let's talk about what lymph is. So, what does all this stuff mean? Well, we're talking about capillaries for a bit, right? So capillaries are what? They're thin. And we're talking about this diffusion and osmosis. I don't even talk about this stuff because I like this picture right here. Let's talk about everything we need to know. So the red stuff is going to be our oxygenated blood on the arterial end, right? So blood is coming into this way, correct? Well, when blood is getting pushed in to capillaries, some of the pressure kind of pushes the blood out into the interstitial fluid. That's going to be our hydrostatic pressure. Hydrostatic pressure on the arterial end is higher than on the venual end. That allows blood to leave or fluid to leave. Does that make sense? Get a little bit of blood pushed out. Luckily, we got some blood proteins, get some big Al's albumin that brings the blood back in through diffusion. You got a lot of proteins that'll solute, not a lot of solvent in there, right? Water's a solvent, so it brings the water back in normally. Does that make sense? Cool. That's how we kind of exchange stuff with capillaries. Now, sometimes we got some tissues up here that will absorb the fluid. The fluid that leaves the arterial end, it is not picked back up in the venual end. That is what lymph is made out of. That makes sense. Lymph is basically just fluid that's outside of our system, inside of lymph vessels and lymph nodes. Does that make sense? That's why it's part of this. That's why I talk about this real quick. That's where lymph comes from and how it's made. Does that make sense? So why do we do this? Well, 10% of all your blood right now is inside your lymphatic system. This is quality control and quality assurance, right? So at any given time, your body's checking 10% of your blood for pathogens. Is that a good thing or a bad thing? Probably a good thing. That doesn't make any sense. Who here has been in the airport or have been to an airport recently? Any of you guys been to an airport recently? Yes or no? You guys drive here?
Yeah.
Where the place you are from? You guys are crazy. Go fly. It's way quicker. But if you've been in an airport, TSA sometimes randomly pulls people away from the line and searches them more heavily, right? That's what the lymphatic system is. It's pulling parts of your blood away to give it a more thorough pat down to make sure it's not acting weird. Lymphatic system. Okay. That's where interstitial fluid comes in. Green stuff's lymph. Kind of gets pulled in. Interstitial fluid is just basically that. It's pulled in, boom, it enters. It can't leave because lymph has valves too. So edema. Edema basically occurs when there's too much fluid in the interstitial places where it's not picked up by lymph. So you got some fluid kind of leaking out. That kind of makes some sense? Is edema good? No. Cause of edema, poor venous return, congestive heart failure. You're not using your muscles, kidney failure. Probably not a good thing. You can fix it though. If you just basically wear compression socks, compress your legs, right? And in severe cases, you have to put these weird machines on. You can compress the legs, push all the fluid back into the veins, hopefully, and back into your heart, make it go back to circulating. Does that make sense? That's why if you've ever been in the hospital to stay overnight, they put these weird socks on you that compress your feet. It's to stop edema from occurring. What's up? So what I'm saying is so fluid leaves, right? And 90% of the fluid that leaves will also enter back in the venule end because of like albumin, globulin, proteins like that, right? But if fluid gets picked up into capillaries, lymphatic system, because it's a one-way door, it can't leave. It's pushed in, right? And then sometimes, due to some issues, right, blood can pool and stagnate, get pushed out interstitial fluid, which is what causes edema. Yep. Make sense? Cool. So, lymph vessels, drain. You got 6 collecting ducts. Subclavian veins are your biggest ones. So it all goes back in the same system. It's still part of your blood. Lymph flows to your heart. It acts like mini veins. It acts basically just like veins. Cool, valves. I'm not really going into this much detail because how they work isn't as important as what they do. It is cooler though. Lacrimeals. So these are lymph vessels that only do one thing. They help reabsorb fat in our body. So if I eat a nice big piece of ribeye steak and this big chunk of fat, my body has a hard time breaking fat down, right? But I like fat. So my body has a hard time absorbing it, so it pushes it out. The lacteals pick it up and recycle it, so it has more chance to being broken out efficiently. Make sense? Kind of recycles the fat in our system so that it has a higher chance of being broken down. Okay, so the lacteals work. So you have primary lymphatic organs, which are basically your lymph nodes. And you have secondary. Sorry, lymph nodes are secondary. Tonsils, spleen of that. Primary would just be bone marrow and thymus, I guess. So secondary is lymph nodes, tonsils, and spleen. Primary is bone marrow and thymus. Okay, so where are lymph nodes located? Pretty much everywhere, right? But mainly you find them around the areas to the trunk, right? A lot of the neck, a lot in the armpits, a lot in the groinal region, right? You find a lot of them there. Lymph nodes are where basically all the lymph is going to collide for a bit. And there you have COPs, because white blood cells basically think of them as COPs. You have macrophages. What do macrophages do? They eat things. They're phagocytes. They eat things. And then you have B cells. And what do B cells do? B cells make antibodies. All right? So the 2 COPs to your lymph nodes are macrophages and B cells, which differ into plasma cells, which is basically just antibodies. Okay, so here's how lymph nodes work. There is a ton of entrances, but only a little bit of exits. Why is that important? Slows down the fluid. Why do I want to slow down the fluid? Yep, I got my Pac-Mans there, right? I got some Pac-Mans, right? There to eat the things they find that's bad. And I got some B cells in there to start making antibodies if they need to. That makes sense? Okay. Lymphitis is inflammation of the lymph nodes. This usually occurs if the macrophages or B cells encounter something inside of them. So if your lymph nodes are swollen, it just means they're doing their job. Now, if they get too swollen, probably not a good thing. The issue with lymph nodes is that if they get cancerous for some reason, bad. Cancer in lymph nodes is bad because they can have easy access to the rest of the body. Kind of make some sense? Cool. There you go. All these little dots right here are lymph nodes. Boom, 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 boom. Swollen lymph nodes, not good. They drain. Tons of lymph nodes in breast tissue. Why? What's the main purpose of breasts? To produce milk. Do you want to feed a baby contaminated milk? Yeah, you want to feed a baby contaminated milk? You just kill the baby. Congrats. Lymph tissue is there to make sure that milk produces good and clean. Next up, we got tonsils, everyone's favorite. these things aren't really necessary, and most of the time they're quite deadly. I don't know why they are here. You leaving? Okay, bye. If lymph nodes swell up, what can happen to your airway?
It blocks it.
Is that good? That's
No.
simply a design flaw, isn't it? That's why most people get their tonsils removed, because they're not really necessary, and they're more of a detriment to your health than anything. They're helpful because they do help contain some lymph nodes. They're the main lymph nodes found when you eat stuff. But it sucks when they swell up because you can't breathe. The spleen. Spleen's a secondary lymph organ. It's going to have mainly macrophages in there to basically kill blood cells. The spleen is where bloods go to die. Gets fixed up. Nice, nice, nice. When you are a fetus, before your red bone marrow is taking place, this is where red blood cells are made. The iron also stores lots of, the spleen stores lots of iron for later uses. That's why you eat the spleen of an animal, it tastes kind of like blood, because it basically just has a bunch of iron in it. There you go. So, the white parts of spleen matter. The white part of spleen matter is going to be where lymphocytes are located. The red part is where blood goes to die. I think the spleen has a bigger purpose. What do you guys think? A lot more red than white, correct? So that's what we want to learn about the spleen. Okay. First slide down. Anyone have any questions for me so far? That part, yes, no, maybe so. Okay, you want like this? Okay, no, okay. Splenomegaly. This means gigantic spleen. Spleen's enlarged for some reason because it is a lymphatic organ. It can get enlarged when dealing with infection. The most common infection that causes splenomegaly is the kissing disease, also referred to as mononucleosis. If you get mono, there is a good chance your spleen will double in size for a bit. It is how the virus progresses in the body. Now, that's not good. Why? What's the spleen mainly do? Break down what? Blood. So there's a lot of blood stored there? Do I want that to rupture? Probably not. So after getting mono, you're told not to do contact sports for about 6 months because your spleen's gigantic. So that's fun to know. How you guys know? This poor little kid, if you look at him, you can see his spleen. That's his spleen. That's not good. He probably doesn't have mono. Probably has some other weird issues going on with him. And notice that someone has splenomegaly, like they just have mono. Hey, thymus. Who has thymuses? Children. This is to help kids basically mature T cells. As you get older, you should not have a thymus because you already have an adaptive immune system already. Cool. So now we're going to actually talk about how the immune system works. The first line of defense is your skin and your mucous membranes. That should make sense, right? Skin, it stops with the outside world. Next up, I have fevers and inflammation to hopefully kill and burn everything. If that doesn't work, last line of defense is the immune system. That kind of makes some sense? Cool. So we're mainly going to talk about the last line of defense. So let's talk about the types of leukocytes. What does leukocytes mean? White blood cells. Do not confuse leukocytes with lymphocytes. Leukocytes are all of these guys. Lymphocytes are their own type. So first, leukocytes is the neutrophils. What's special about them? What's special about neutrophils? They are the most numerous. They are the most common. They have the highest numbers. Heading out. Bye. they're mainly going to be focused with bacteria. This makes sense because these are the most common. They're mainly going to fight bacteria infections. Make some sense? Cool. How they fight things is lysosomes. They're going to basically cause things to blow up. Nice, peroxide and such. Eosinophils. They have two targets, parasites and allergens. I want you guys to focus more on the parasites parts. I'll tell you why in a little bit. So what do you think? What do you think you find eosinophils more likely to find them? Where do you find more parasites in your body? In your stomach and your intestines. Eosinophils are mainly going to hang out there. They do things with allergens. They mainly turn on the next one, which is basophils. Basophils are going to release histamines, right? But I want you guys to know more about basophils for allergens, right, than eosinophils, because basophils make histamines. And histamines are what cause you guys to get a cloggy nose and all that stuff, right? You guys take Claritin, right? That's an antihistamine. So it turns off your basophils and such like that. Does that make sense? Cool. Monocytes. Here's where things get weird. Monocytes are macrophages, but they change the name of macrophages depending on where they're at. If they are in the blood, they are monocytes. If they are found somewhere else, they are macrophages. Macrophages then can be specialized even further. Dendritic cells are found in areas exposed to the environment. So, skin, mouth, esophagus, and other areas open to the skin. You can read the highlighted parts, hopefully. Does that make sense? Why would it have dendritic cells in these places? Yes or no? I'm getting these weird stares. I know it's only been 2 hours, guys.
Yes.
I know. Okay. Microglial cells. We learned about those last semester. Those little things in the brain that help destroy bad brain tissue. You got some alveolar macrophages found in that, some stuff found in the liver. Monocytes when in blood, macrophages when found somewhere else. Up next, lymphocytes. These are the T cells, B cells, and NK cells. So these are specialized cells. Does that make sense so far? All this kind of making more sense, you guys? Okay. So before we talk about those cells, let's talk about how things fight. So how lymphocytes mainly work is they're going to cause pathogen destruction. They can cause it short term by interferons in the complement system, right? Interferons, quote unquote, the dying words of something. So when a cell gets infected and starts dying, it starts telling it, I'm dying, and it starts kind of screaming out. Basically, these are death thralls of cells, and they alert all other cells that they are dying and infected. These call in NK cells. What are NK cells? Natural killer cells. What do natural killer cells do? It's in their name. They kill things. They kill things almost nondescriptly. They will start stabbing everything and basically causing purfurons to just start stabbing things, causing things to blow up and kind of like a balloon, like popping a balloon. So that's what interferons do. If there are types of interferons, you don't need to know between alpha, beta, and gamma. But just know that they talk to other things and call in natural killer cells and macrophages to start killing things. The complement system. So if I were to give you a compliment, what does that mean? I'm aiding your self-esteem. I'm boosting your ego, right? It means I'm kind of helping you if I give you a compliment. It makes you feel better. The complement system is two different things. You have an alternative pathway and a classical pathway. If I were to go down the street right now and ask someone how the immune system works, 95% of them are probably going to talk about antibodies, right? That means that's the classical way of thinking about it. Because classically, you think about antibodies. Now, the immune system also has non-specific ways, which are going to be the alternative pathway, which complements the classical pathway. Does that kind of make some sense way of thinking about it? Justin, you give me a weird look. What's up? Make sense? You're like, you give me a weird, like, I don't know, look. Okay. Oh, okay. It looks like you're itching your nose. Okay. So, what's going on here is blah, 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 blah. This guy pops onto the cell wall. Alternative pathway begins when several components, proteins, whatever, this is triggered by blah, 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 blah. Basically, this guy goes in the cell and kind of pokes a hole in it and kind of signals something is bad. Antibodies do the exact same thing, but they work independently of each other. And sometimes they can aid each other and complement each other. That's why it's called a complement system. That makes some sense? Cool. We'll talk about MAC in a little bit. Inflammation. So inflammation is basically going to be, you're going to increase heat. What are the signs of inflammation, guys? You guys remember from last unit, last exam?
Yeah.
Rubor, calor, dolor, tumor. Redness, swelling, pain, and increased heat for calor. Basically, cytokines are going to increase the heat of the body. The reason we're doing this is because we are big organisms. Can we handle a good increase in temperature? Yes or no? If I pull someone from Texas right now where it's snowing like crazy, like a blizzard, and I go throw them in the middle of the desert, are they going to start dying due to the temperature change? No. Little tiny organisms like viruses and bacteria cannot handle a huge difference in temperature change. Our body's really good at doing that. So the reason we have an increase, increase in temperature to deal with infection is probably to start burning them up and try breaking down their proteins and such. That's why we do that. Heat, pain, all this stuff is caused by that stuff. There's your sensations. Fever. Cytokines do that. So you want at least a fever below 105. Anything higher but 111 or so, going to cause your brain to start melting, cause coma and death. We can handle a little bit, right? Because like 98 is a good temperature for humans, right? We go all the way to 105. 115, not good for us. It's going to kill your brain. Sometimes your body's not going to work correctly and kind of act stupid, and you're going to increase it too much and basically overheat your brain. Does that make sense? Okay. Now we're back onto this. So if your teacher likes to use analogies, NK cells, they probably call them like beat cops. They travel around the bloodstream and look for crime. I don't like that because NK cells kill everything they come in contact with. They're serial killers. They're natural born killers. They kill bacteria cells. That's great. Transplanted cells. That's not so great. Cells infected by viruses. That's good. And cancer cells. That's good. So they aren't like knowing what they're doing. They just go around stabbing things. They do this by doing purfurons, which punches a hole in the thing, causing the cell to leak. And then they have these little enzymes that start breaking things down and cause apoptosis to occur. That makes sense? Cool. Oh, that's how NK cells work. I don't like this because it jumps around a lot. If something is innate, what's that mean? Are you born with it or you have to learn it? You're born with it. Maybe it's make-believe. Maybe she's born with it. So, are you born with skin? Hopefully you are. That'd be a scary, ugly-ass baby if it wasn't born with skin. You have macrophages, neutrophils, basophils, all those are already part of your immune system, right? You already have NK cells, you already have interferons, already have the complement system, right? Or the alternative pathway. You already can make fevers. Babies can already have fevers, right? This is innate. The next thing I'm talking about is going to be adaptive immunity. This is going to be memory T cells, B cells making antibodies, this type of stuff. Does it make sense? That's what they kind of talk about it. So NK cells, they kill things. B cells make antibodies. To make an antibody, it takes a long freaking time to do that, though, right? So they always tend to come late. Memory T cells. What do you think they're good? What do you think they have good? What do you think they have good of? That's good memory. Good. I can't speak right now. It's talking for 3 hours straight causes brain to go burr. Okay, memory T cells. They remember what they fought against so they can easily fight against it in the next time. Does that make sense? This is why once you get infected with the chicken pox, you can't be infected with the chicken pox again because your memory cells stop it from happening. Does that make sense? But diseases like the flu, they keep on changing. So memory T cells don't help too much with them. Good. Helper T cells, what do you think they do? They're pretty helpful. They are the mom and dad of the group, kind of. You already have these as friends, probably. They make sure everyone's waking up and eating their food and doing the laundry, right? You probably have friends like this, don't you? If not, get a friend like this. They're nice and sweet. Helper T cells get the other T cells going because they take forever. They motivate them and get them going. My favorite type of T cell is the suppressor T cell. It suppresses your immune system, which you think is weird. But after you get infected with the flu, after a week of being infected, does your immune system still need to go in overdrive? Yes or no? No, it doesn't. You already fought the infection. You're not infected anymore, right? And hopefully you should be infected for a while. So your suppressor T cells start making everything go to sleep and suppresses them. If we didn't have suppressor T cells, you have a higher increase of autoimmune diseases. I think that's pretty interesting. What do you guys think? Cool. And then you have your cytotoxic T cells. These guys are kind of boring. They're the normal type of T cells. They start acting like neutrophils. You see eosinophils, basophils. They start acting like those guys go start fighting infections. They just take a while to get going. That make sense? Okay.
Did you say B cells make antibodies?
Yes, B cells make antibodies, but it takes time to make antibodies. Okay, so cellular immunity, T cells, hormonal, it's going to be B cells because antibodies. So let's talk about MAC or MCH. So there's class 1 and class 2. So what's really cool about our cells is anytime they make something, they take a piece of that protein or enzyme and they shove it outside their self, and this they show the rest of the body, this is what I'm making. Does that make sense what I'm saying? Basically, you guys turn homework in, that tells your instructors what you guys are doing in your free time, what should be studying, right? Right? You guys are students. Most of you are my students. You should be studying for my classes, which is nice. If a cell is cancerous, it's not doing anything except multiplying. It doesn't show anything. So when an NK cell walks on by, it goes, hey, what are you doing? It goes, I'm not doing anything. And the NK cell goes, good, and starts stabbing it and killing it. How NK cells work. The cell gets infected by a virus or bacteria. It starts making little tiny viruses and bacteria and starts shutting out of the cell. NK cell goes, whoa, 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 I don't like that. Starts stabbing it. That's how that works. Does that make sense? That's what class 1 infected MCH proteins do. And class 2, only phagocytic cells like macrophages have these. So when a macrophage eats something, it then will go show it to a B cell. So you guys were as kids play the you like seafood game where you eat food and go, you like seafood, and you go, Dad, and you show the food to your friend. You guys ever do that in grade school at all? No? Well, I babysat my nephew the other day. That's what he did 3 times in a row. I think the lack of socialization is bad for him. He's turning into a really weird kid. So when a phagocyte eats something, it shows it to a B cell. Why would I want to show what I ate to a B cell? The B cell goes, oh, that's not good, and starts making antibodies. That makes sense? That's why macrophages in B cells are found in lymph nodes. So this can easily happen really quickly. That makes sense? Ah, it's all coming together again. Bum-ba-da-dum. Cool. This is basically talking to a macrophage, talking to a B cell. Sometimes what will happen is that after a cytotoxic T cell encounters something, right? It'll bump into a macrophage. Macrophage goes like, here you go, remember this. And then it basically just remembers it and becomes a memory T cell forever. Because those are the only type of T cells that survive after an infection's over with, memory T cells. Cool, cool. And those usually occur because of CD4 T cells or helper T cells. So they also can help make their friends remember things. Aw, aren't they sweet? Cool. Oh, here's a better way of memorizing it. I like this way better. So macrophages do talk to B cells, but they have these T helper cells also. They can also talk to T helper cells, which then tell either cytotoxic T cells or B cells what's going on too, right? This doesn't occur in lymph nodes. This occurs in blood, right, where infections can also occur. That kind of makes some sense, what I'm saying? Yes or no? Okay, I just told you that macrophages talk directly to B cells, correct? That mainly is going to occur in lymph nodes. Do you think most infections occur in lymph nodes or in the blood? Probably in the blood, right? So in the blood, macrophages talk to T cells. T cell goes, hey, I'll carry that for you, right? The little piece of protein it just ate from the virus. It then will either go to a cytotoxic T cell and go, hey, can you do me a favor? Can you remember how to fight this? And that becomes a memory T cell. Or the helper T cell can go bring it to a B cell and make it make antibodies. It just has a chance of making memory T cells this way. Does that make sense? Yes or no? So how memory T cells are made. This usually occurs the first time you get infected with something. Okay. Antibodies. They look like a Y, and that's good because they have two attachment sites. And once they attach, they cannot unadhere, which is a good thing because they basically swarm or coagulate around viruses and bacteria, such as this. Cells can only do something when their binding sites are open. Antibodies close up because they block the binding sites. Sorry about that. Basically, they surround and suffocate viruses and bacteria for what they want to do. Okay, here's what it looks like. Well, here's what it looks like underneath an electron microscopic lens. Okay, here we go. We're going to talk about these things. The most common type of antibody is IgG. IgG are what are made by B cells. These are specialized immune cells. These are going to go target specific viruses and bacteria. If I were to take your guys' blood right now, if you are not sick, you should have low amounts of IgG. Does that make sense? If I were to take your blood and you have high amounts of IgG, what's that tell me? You're probably sick. Does that make sense? So, COVID testing, rapid testing, they are just testing to see if you have the antibodies for COVID. Your body is making antibodies for an infection. Does that make sense? That's what a rapid test is for. It takes a while before this test becomes, before you can be tested for COVID after being infected by it, because it takes time to make the antibodies. That makes sense? Cool. I don't think IgE and IgD are that important. The next biggest one I want to talk about is IgM. If you're not infected, this becomes the highest concentration one found in your body. This is the one that reacts to blood. So what are the three types of blood groups you guys have? There's 6, but that's positive Rh factors. ABO, right? And AB positive, and AB, O, and AB, right? If you're O, you don't make these. If you're A, you make the B version. If you're B, you make the A version, basically. That kind of makes sense? Sorry, if you're O, you make both of them. My bad. Misspoke. Been going on too long. So basically, these are going to be in your blood at any given time to do that. That's what these do. But these are not the ones that cross the placenta. Those are going to be the top ones up here. IgG cross the placenta because they're so small. IgM is too big. Okay, what else we got here? That's basically an overview of everything. We talked about all that before, how B cells do things. Aha, how vaccines work. The vaccine takes a weakened, basically weakened version or dead version of the thing, injects it into you. Macrophages find it, eat it, and then bring it to a T cell and B cell. Don't make antibodies and memory T cells to how to fight that thing. That way, when you counter it for real, you're much better. That makes sense? Okay. This is going to stimulate your active immunity, which is going to help you basically fight things, which vaccines are active immunity. Passive immunity is when you receive antibodies from someone else. So a good way of what some people did is when they were sick with COVID, they made antibodies of COVID. They could take the antibodies out of the blood and inject it someone else. The issue is since the person who got injected with the antibodies has not been compromised by the virus, they don't know how to make the antibodies themselves. It's only temporary. That kind of makes sense? This also occurs with babies. The mom is going to give the babies antibodies to help fight infections sometimes, right? Breast milk is heavily involved in this, which is why you should feed babies breast milk. That's why most mammals need to use breast milk because of this. And that's how that works. Sometimes you can just give someone human tetanus, basically antibodies. Allergies, where IgE comes into play. These are overreactive to everything, release histamines. Now, sometimes you can be born like Bubble Boy, which isn't his real name, I forgot his real name was, but he was called Bubble Boy because he lived in a bubble. He lacked T and B cells. He could not make antibodies. He could not remember infection. So every time he got infected with something, it was the first time he got infected with it. He had almost no immune system because of that. Does it make sense? That's why he was very vulnerable to outside infections. AIDS will kill helper T cells, which slows down infections. Please know this, AIDS leads to HIV, which basically means no T cells, helper T cells. If you don't have helper T cells, you stop making memory T cells, and your T cells become too slow to react to most infections. That makes sense? Okay. And then leukemia. Leukemia is cancer of the white blood cells. That's not good. If you have cancer in the white blood cells, probably going to mean less white blood cells, which means higher risk of other infections. Okay. Anything else you guys got?
My teacher told me that I should know like what they use to like suppress HIV from turning into full-blown AIDS.
Oh, that drug. Okay. So HIV treatments. So you can't treat it. You can suppress it. You're going to give a bunch of drugs, but mainly these ones right here. You're going to give protease inhibitors, which should slow down protein of HIV, and it's going to slow down any remaining T cells you have in your body. And adenosine is going to help reverse anti-transcriptase. Those are the drugs I would recommend knowing for HIV at least.
Okay, thank you.
Yep. Cool, cool. You teachers talk about anything else I did not cover? Is that everything? Okay, it only took us almost 3 hours. Cool. Michael, any questions for me? Darius, any questions for me?
I don't have any, I'm probably just gonna go over my study guide again and some questions she asked us in class.
Okay.
And she over stuff today.
Yeah, if you have any questions, just email me.
Okay.
I did record it. Yes, I'm going to post it.